Okay, please, it's Dr. Oisin McCormack. The stage is yours.
I want to build a star. The sun is our ultimate source of energy. Life on Earth exists because of the light and heat we receive from it every day. Fusion energy is what powers our sun, where heavy hydrogen atoms, called deuterium, are so hot that when they collide, they fuse together, releasing massive amounts of energy. This deuterium fuel is 5 million times more energy dense than fossil fuels, and it is naturally present in all water everywhere, even in these bottles of water here. To give you an example, whoever has flushed their toilet this morning, you've just flushed away about 0.5 gram of deuterium, which is enough fusion fuel to power your entire house for 3 years. With such a clean and unlimited energy source, we could end war, end famine, stop climate change, even start to build cities on other planets. 5 kilometers from here, in my office, we have a fusion reactor. It looks a little different than a star. It's about 10 meters in diameter, and it's in the shape of a donut. And inside our donut, we have our deuterium plasma fuel that is suspended in mid-air by magnets. This fuel is heated up to 15 million degrees, the same temperature as the core of the sun. But how do we measure such huge temperatures? Well, that's my job. This is me here, the tiny me down there. I shoot a laser into the reactor, which bounces off the fuel. This bouncing is called Thompson scattering. So before scattering, the wavelength of the laser line up in the top right corner looks like a straight line. But when the fuel scatters it, this laser line gets stretched. And the wider it stretches, this means the hotter the fuel is. So we can measure the temperature of the fuel from the width of this curve, and we can also measure the density of the fuel from the area underneath the curve. The temperature and the density are 2 vital measurements for controlling the reactor and achieving fusion. In my PhD, I developed advanced Thompson scattering techniques. My main project so far was, instead of using a single laser, I took 2 different lasers and combined them together onto the same path. This gives us a double measurement that is both self-calibrating and more accurate than the single laser method. I was the first person in the world to test out this technique, and it is now being included in new, bigger fusion reactor designs. Fusion is the future, and my job is to help build it.